welcome you all to another video lesson on Markov Chains. In this video lesson, we'll look at a few problems solved by using the Chapman Kolmogrov Equations, specifically designed for Markov Chains. Throughout this video lesson, we'll denote P the superscript of 0 as P naught, which denotes the initial probabilities of the various states in the Markov chain, and we'll denote the transition probability matrix by M. So when we know information about these two, P naught and M, the probabilities that the system is in a particular state after n time steps or after n transitions can be calculated by using Chapman Kolmogov equations. To give you a hint of how these equations work, we look at this P1, which is the probability after one time step. We multiply the initial probability P naught with the transition probability matrix. To find P2, we multiply P1 by M, or effectively, we multiply P naught by M square. Similarly, to find P3, we multiply P naught by M cube. We can generalize this and arrive at the expression for Pn, the probabilities after n time steps. To get these probabilities, we can multiply P naught by the n power of the matrix M. To give you a hint of what is happening here, I'll first do a simple problem and then we'll look at other complicated questions. So let's consider a Markov chain whose TPM is given here. There are three states in the state space of the Markov chain, 0, 1, and 2. And their one-step transition probability matrix are given by M. So M is a 303 by 303 column matrix, which denotes the one-step transition probabilities of the states in this Markov chain. The initial probability that the system is in one of these states is given by 1 by 3, 1 by 3, and 1 by 2. We follow a particular sequence and we stick to the sequence throughout this video lesson. The question before us is to find out the chance that P of x2 is equal to 2. Now, how do we understand this P of x2 is equal to 2? P of x2 is equal to 2 will denote P of x2 is equal to 2 will denote the probability that the system is in state 2. System is in state 2 after two time steps. So the number on the right is the state that we are in, and the number in the subscript is the number of time steps. This is the time step. This is the state that we are in. So the first problem wants us to determine the probability that the system has reached state 2 after two time steps. And to calculate that, we will use the Chapman Kolmogrov equations. Since two time steps have elapsed, we will find out P2. And to find P2, we'll need P1. And to find P1, we'll need P0. P0 and M are as given in the problem. We multiply this 1 by 3 matrix and the result then the 3 by 3 matrix, which means P1 is again a 1 by 3 matrix with answers as 4 by 12, 6 by 12, and 2 by 12. So this is the answer for P1, the probabilities after one time step. So after one time step, the system is in state 0 with a probability of 4 by 12, in state 1 with a probability of 6 by 12, and in state 2 with a probability of 2 by 12. Now this is after one time step. Since the question wanted us to discuss two time steps, we'll proceed with this once more. So P2 will be P1 times M, which is again the product of two matrices of order 1 by 3 and 3 by 3 respectively. The resulting matrix is of order 1 by 3 and that's the answer 18 by 48, 22 by 48, and 8 by 48. And since we are focused on the state 2, our required answer is 8 by 48, which is known as 1 by 6. That solves the first question. The second question wants us to find this probability. Now, this is a pretty interesting question, and it will be more interesting if you can follow as to what exactly is asked. It says after three time steps, the system should be in state one. But also, the comma here is to be understood as an intersection symbol. The comma here is to be read as good as intersection. So it is as good as having this is equivalent to P of x3 is 1 intersection x2 is 2 intersection x1 is 1 intersection x0 is 2. So after three steps, it must be in state 1. But not just that, we also want the system to be in state 2 after two steps, state 1 after one step, and it must have all began from state 2 at the start of the process. So to do this, we'll follow the conditional probability tool, which we learned when we discussed Bayes' theorem, where the intersection probability is understood in the form of conditional probability and the basic probability. So I'll just draw your attention to the formula that we learned in Bayes' theorem. P of A given B is P of A intersection B and P of B, or in other words, P of A intersection B is P of A given B is this P of A intersection B divided by P of B, which means the probability that we wish to find out can be easily determined as the product of the conditional probability and P of B. And determining the conditional probability is easy if you can refer to the TPM, the transition probability matrix, for every one step transition. So here I'll follow this technique. So x2 must have been at 2 and x3 must have been at 1. So the system should have been in state 2 after 2 steps and it must have moved on to state 1 after 3 steps. So from 2 to 3, there is only one time step happening, which means this can be denoted by P to 1. So this was in state 2. This has moved to state 1. And we'll rewrite the other probabilities in the same way. This was in state 1. It has moved to state 2. So the probability here will be P12. This is P12. And this was in state 2. This has moved to state 1. That is P21. And it must have started with state 2, which means P of x0 must be 2. So we know the last part from the question. All initial probabilities of the system being in any of the states is 1 by 3. So this answer is pretty obvious. To find these three answers, we'll use the transition probability matrix. From the transition probability matrix, moving on from state 1 to state 2 is this entry here, which is 1 by 4 in one time step. Moving on from state 2 to state 1 in one time step is given by 3 by 4. So the probabilities that we move from 1 to 2 in one step is 1 by 4. From 2 to 1 in one step is 3 by 4. Once we have known these two answers, we can directly substitute them in the formula that we just derived. So we'll have 3 by 4 times 1 by 4 and 3 by 4 times 1 by 3, which means our required answer is at 3 by 64. That completes the answer. So this is how we know that we have used the Chapman Kolmogrov equation to find the probabilities of subsequent time step transitions using the TPM. We'll move on to some advanced questions next. One such question will be this. Suppose that the probability of a dry day, state D, following a rainy day is 1 by 3. The probability of a rainy day following a dry day is 1 by 2. And given that March 1 is a dry day, find the probability that March 3 is also a dry day and also find the probability that March 5 is also a dry day. So this is a classic example of a Markov chain where we usually try to model the weather of a given city on a given day based on the weather of the previous day. So there are two states here. A given day could be a rainy day R or a dry day D. And the problem also tells us that March 1 was a dry day. Since March 1 is a dry day, we begin with the initial probability matrix as 0, 1. So if we know for sure that March 1 is a dry day, so the corresponding P naught is 0 and 1. And we are also given that if day 0 is a dry day, day 1 is a dry day with a probability of half. And if day 0 is a rainy day, we know that day 1 is a dry day with a probability of 1 by 3. So that gives us enough clue to define the TPM of the matrix as follows. So a rainy day followed by a rainy day has a probability of 2 by 3, and a rainy day followed by a dry day has a probability of 1 by 3. Similarly, a dry day followed by a dry day has a probability of half, and a dry day followed by a dry day also has a probability of half. So this is the TPM, and we use this TPM to arrive at the required answer. We note that March 3 is 2 days away from March 1. The 1st of March is the given initial data, and we're asked to find it for March 3. March 3 is 2 days away. So from P naught, we'll move two time steps to reach P2. So one time step will end us, will end up on March 2nd, but we don't want data about March 2nd. We need data only about March 3rd. So one time step at a time, we'll go to March 2 and then go to March 3. Or if we directly compute two time steps, we'll directly end up in March 3. So we need P2. Like we said before, two time steps have been calculated. So we need P2 from P naught. Now I'm going to discuss two different methods in which you can do this so that based on the problem and the size of the problem, we can choose whichever method is convenient to us. Method 1. Method 1 is to find the square of the matrix, the transition probability matrix, and multiply that by the P naught. So we have the TPM as we defined in the previous screen, 2/3, 1/3, half and half in the second row. We get the square of it. The square of it comes down to 11 by 18, 7 by 18, 7 by 12, and 5 by 12. Now, by the Chapman Kolmogrov equations, we know that this is the direct result by the Chapman Kolmogrov equations. To get P2, we just need to multiply P naught with m squared. So P naught is of order 1 by 2, and P2 is of order 2 by 2. So the resulting matrix is also a matrix of order 1 by 2. We get 7 by 12 and 5 by 12. And we know the sequence in which we define P naught R followed by D. So the first state is the rainy day R, the second state is a dry day D. So we get the required answer to be 5 by 12. So the chance that March 3rd was a dry day is 5 by 12. That's pretty easy. And once again, let's also calculate what happens on March 5. March 5 is 4 days away from March 1. So we need to find P4. So P2 was 2 days away. That was March 3rd. P4 was 4 days away. That's March 5. So we can also do this by finding the fourth part of the matrix. And since this matrix is of order 2 by 2, finding the fourth part is not a difficult task. So we find m power 4, which is the square of m square and n square. Calculating the m for the fourth part of the matrix, we get the matrix as 389 by 648, 259 by 648, 259 by 432, and 173 by 432. Once again, by using Chapman Kolmogrov equations, we can multiply P naught and m power 4 and arrive at these two as the probabilities. So the 5th of March is a rainy day with a probability of 259 by 432 and a dry day with a probability of 173 by 432. And since the question wanted us to focus on the dry day, then we know that probability that 5th March is a dry day. 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 It's 173 by 432. So these two calculations were easy because we found the parts of the transition probability matrix according to the requirement. In one case, we found the square, and the other case, we found the fourth part of the matrix. That was pretty simple. But this may not always be the case. We may have a transition probability matrix of a bigger order. When the order is large, finding the square or higher parts of M may not be that simple, for which the second method can come in handy. And how does the second method work? We don't define the entire matrix. We only follow what the Chapman Kolmogrov equation says. So to find P1, we find P0 and M and multiply both. And here, this is P0, as we discussed before. We began with a dry day, so that has a 0, 1 entry, and the 2 by 2 matrix, which define the TPM. The product of these two gives us half. So March 2nd could be a dry day, could be a rainy day, with a probability of half and half. And with P1 having been found out, we can also find P2. Once again, the same technique can be followed. We know that this is the chance that March 3rd, March 3rd is a dry day with a probability of 5 by 12 and a rainy day with a probability of 7 by 12. This answers our first question. So the probability that March 3rd is a dry day is 5 by 12. We can compare that this answer was the same that we obtained a few slides before. March 3rd is a dry day with a probability of 5 by 12. So this completes this. And we'll go to P4 again. To find P4, we need P3. And to find P3, we need P2. P2 is what we have already. So we'll find P3 as the product of P2 and M. That comes down to this. So this tells us that the 4th of March is a rainy day with a probability of 43 by 72 and a dry day with the probability of 29 by 72. But we are interested only on the 5th of March. So we'll do one more time step. And so P4 can be obtained as the product of P3 and M, which comes down to 259 by 432 and 173 by 432. We want it to be a dry day, so our required answer is 173 by 432. We can also compare this with the answer that we obtained from step 1, which also said the probability is 173 by 432. So this way, the required probability can be obtained based on the size of the matrix. The matrix is small enough and you have the computational power to find higher powers of the matrix. You choose method 1. Or if the matrix is very large in size and computing the higher powers is a meticulous task, you can choose method 2. The next problem I wish to discuss is the problem based on a scenario of a gambler betting in a game. The question goes as follows. A gambler's luck follows a pattern. If he wins a game, the chance that he wins the next game is 0.6. However, if he loses the current game, the probability that he loses the next game also is zero point 0.7. And we are given the extra information that there is an even chance the gambler wins the first game. With all this information, we need to find out the probability that he wins the second game and the third game. Fine. How does this work? First up, since we are talking about the first game, the second game, and the third game, we'll call the initial probability matrix as P1 and not P1 because there is no zeroth game. So the first game, he's having an even chance of both winning and losing. So P1 is half and half. The first chance is for winning, and the second chance is for losing. And now the extra information in the question says that if he wins a game, he wins the next game with the probability of 0.6. So a win is followed by a win with a probability of zero point 0.6, which means a win is followed by a loss with a probability of 0.4. So if he wins game one, he loses game one with a chance of zero point 0.4. If he wins game one, he loses game two. He wins game two again with a probability of 0.6. Similarly, if he loses game one, he loses the next game also with a chance of zero point 0.7. And if he loses game one, he wins game two with a probability of 0.3. So these pieces of information are enough to define the TPM of the matrix, which is at a 2 by 2 matrix, 0.6, 0.4, 0.3, and 0.7. And we want to know the probability that he wins the second game. So that means we need to find P2. So we use the Chapman Kolmogrov equations. P2 is P1 and M. We know what P1 is. That's half and half for both. And we know what the TPM is. Multiplying these two gives us a 1 by 2 matrix where he wins with the probability of 0.45 and loses with the probability of 0.55. He wanted to win the game, and that probability therefore is 0.45. And to find the chance that he wins the third game, we need P3, and to find P3, we need P2. That's again an answer we just found out. So multiplying P2 on M, we get the probabilities as 0.435 and 0.565. 435 is when he wins, 0.435 is the probability that he wins the third game, and 0.565 is the probability that he loses the third game. We talked about winning, therefore the answer is 0.435. But since this matrix is of a very small order, we could also arrive at the same answer by multiplying the matrices. For P2, you need P1. That's a direct answer, which we just did some time back. And for P3, you can arrive at the answer by squaring M. And we know what M is. Squaring of M results in this 2 by 2 matrix. And to find P3, we could directly multiply P1 and M squared, which also gets us the same answer as the probability being 0.435 for winning and 0.565 for losing. So this completes the problem, which says that he wins with a chance of 0.435 and loses with a chance of 0.565. The next topic which I'd like to discuss is the probability of a steady state in a Markov chain. Now, in a Markov chain, a steady state refers to the situation where the probabilities of the states remain unchanged in a Markov chain. And this is observed whenever a Markov chain is ergodic. We've already discussed what an ergodic Markov chain is in the previous video. All states of the Markov chain should be non-null persistent and aperiodic. Once these two are observed, then every state is ergodic and the Markov chain is also ergodic. And whenever the Markov chain is ergodic, the probabilities of the states will remain unchanged when this particular situation of a steady state is attained. So how do we connect this mathematically? If pi a, pi b, etc., pi n denote the steady state probability of the states a, comma b, comma n, then by the definition of what happens in a steady state, we observe that the probabilities do not change. They were pi a, pi b, pi n, and they are also pi a, pi b, pi n after multiplying with the transition matrix. So the one time step that has elapsed does not affect the probabilities, and that's what we mean by a steady state. The probabilities are independent of time. Plus, what do we know about pi a, pi b, and pi n? We know that they are probabilities of a set of all exhaustive, mutually exclusive events. So their grand total will always be 1. So this is the scenario when steady state situations are applied to Markov chains. Whereas when it comes to problems, the steady state is usually referred to by this common phrase: steady state is referred to as the state in the long run. So, in the long run is the code for the steady state being attained. State in the long run. So, when we are facing a problem and they want us to determine the probabilities in the long run, they indirectly want us to calculate the steady state probabilities. I have two problems under this time. We'll discuss them shortly. Question 1 talks about the studying habits of a student. A student's study habits are as follows. If he studies on one night, he's 70% sure not to study on the second night. And if he does not study on the first night, he's 60% sure not to study on the next night as well. So based on this, we are asked to determine the probability that he will study in the long run. So what is the chance of the student studies in the long run? So as discussed in the problem, there are two states in this Markov chain: the chance that he studies, the chance that he does not study. And based on the description, if he studies on day one, he will study on day two only with a 30% chance, and with a 70% chance, he'll choose not to study. And if he does not study on day one, he will continue to not study with a chance of 60%, but he will study with a chance of 40%. So this helps us define the TPM of the matrix, a 2 by 2 matrix in this form. So M has two rows and two columns given by these four entries. And by looking at the TPM, we can arrive at a few conclusions. The Markov chain is finite. There are only a finite number of states, and the chain is also irreducible, and both states are aperiodic, and hence we know that this Markov chain is ergodic. And because the chain is ergodic, we can apply the concept of the steady state probabilities here. So we'll call the two steady states, studying and not studying, as 1 and 2. So their steady state probabilities are phi 1 and phi 2. So phi 1 is the probability that the probability that the student will choose to study, and phi 2 is the probability that the student will choose not to study. So when the steady state is reached, we know that phi 1, phi 2 in product with M will return in phi 1, phi 2 as the probabilities. The transition will not have any effect on the probability. And in addition, the sum of the two probabilities will always be 1 because there are only two chances and they are exhaustive and exclusive. So applying this condition to the transition probability matrix that we define, we arrive at two equations in terms of phi 1 and phi 2. This is simple matrix multiplication. 0.3 phi 1 plus 0.4 phi 2 is phi 1 again. And 0.7 phi 1 plus 0.6 phi 2 is phi 2 again. Simplifying, we see that phi 1 and phi 2 are connected by this equation. Phi 1 is 4/7 of phi 2. Phi 1 is equal to 4 by 7 times phi 2. And we know that their sum is 1. So applying this substitution, we apply this substitution, the one in this blue box, to this equation, and that helps us solve for phi 1 and phi 2, where we observe that phi 1 is at 4 by 11 and phi 2 is at 7 by 11. So in the long run, he will choose not to study with the probability of 7 by 11, and he will choose to study with the probability of 4 by 11. This is how we calculate the probabilities when the steady state is attained. So these are the answers in the long run. So this is how we compute. So all we need to do is apply the concept and just solve for the unknowns. The unknowns will be the probabilities, which will be equaling the total number of states in the Markov chain, and that will help us find that phi 1 and phi 2. And this is easy to solve. This is a system of equations which can be solved easily. All right, for our next problem, we'll discuss a similar scenario where we discuss the tour plan of a tourist across three cities A, B, and C. The description is as follows. A tourist's tour plan contains three cities A, B, and C. He never visits the same city on successive days. He visits city A, then the next day he visits city B for certain. However, if he visits either B or C on day one, then the next day he's twice as likely to choose city A as the other city. He's twice as likely to choose city A as the other city. How often does he visit each of the cities in the steady state? So the question wants us to find the probabilities that he will choose either of the three cities in the steady state. So it's obvious that the states of the Markov chain will include the cities in the tour plan. So A, B, and C are the three states of the Markov chain. The question says he never visits the same city on successive days. So if he is in A, he'll not be in A on the next day. So All the elements along the principal diagonal are zeros. And if he visits city A, then the next day he's to choose city B for sure. So from A to B, the chance is 1. And if he's either in B or C, he will prefer A to C with a twice as likely probability. So if he's in B, he'll go to A with a chance of 2 by 3 and to C with a chance of 1 by 3. Obviously, he'll not go to the same city the next day. Similarly, if he's already in state C, he'll go to A with a chance of 2 by 3 and B with a chance of 1 by 3. So this helps us define the TPM of the matrix, the 3 by 3 matrix with all elements along the principal diagonal being 0. And the question wants us to calculate the steady state probabilities directly. We just once again examine and find out that this Markov chain is in fact finite, irreducible, and all states of the Markov chain are aperiodic. Therefore, the states are also ergodic. And because of the ergodic nature of the Markov chain, we know that we can apply the concept of the steady state probabilities here, which we can do. So let's denote phi A, phi B, and phi C for the probabilities in the steady state for the three cities A, B, and C. And by applying the concept of steady state transition, we know that the probability will remain unchanged even after one time step. So what was phi A, phi B, and phi C will remain at phi A, phi B, and phi C even after multiplying with the TPM. This gives us a system of three equations this time. Unlike the last time where we had only two equations, we get three equations by multiplying the matrix. So this is for the first row, first column, for phi A, for phi B, and phi C. And in addition, we also know that the sum of the three probabilities will be 1 because these three states are mutually exclusive and exhaustive. We have phi A plus phi B plus phi C is equal to 1. So we have a system of four equations here, and we can solve them pretty easily to get the answers for phi A, phi B, and phi C. The third equation is pretty helpful here. Phi B is 3 times phi C. We can apply that to show that phi A is 8 by 3 times of phi C. Substituting them in equation number 4, we get phi C as 3 by 20, which will help us find phi A as 8 by 20 and phi B as 9 by 20. So in the long run, the tourist will visit city A with a chance of 8 by 20, city B with a chance of 9 by 20, and city C with a chance of 3 by 20. So this helps us easily find out the steady state probabilities. It just boils down to solving a system of equations. So if we can define the TPM properly, then finding these probabilities is not a big task. Okay. And I'll follow this with one problem, which is pretty popular among questions in Markov chains. It's called the gambler's ruin. It discusses what happens when a gambler has a particular pattern of luck. So let's read the question again. A gambler has rupees 3 at the start of a betting sequence, and he follows this pattern. At each bet of the game, he loses rupee 1 with the probability of 3 by 4, but wins rupees 2 with the probability of 1 by 4. So he is winning 2 rupees or losing 1 rupee. And he stops betting if he has lost his initial amount of rupees 3 or he has won at least 3 more rupees. Now, our question is to write on the TPM of the Markov chain, which explains the given situation, and also find the probability that there are at least 4 bets. To do this, we'll understand the problem in detail and then proceed. So the gambler wins 2 rupees with a chance of 1 by 4 and loses 1 rupee with a chance of 3 by 4. The states of the Markov chain here are the money he has at the end of each bet, and that will help us define the TPM and the initial probability matrix. So the minimum amount that he can win is 0 because The question says the gambler quits betting if he has lost all 3 rupees that he began with. So to lose 3 rupees after starting with 3 rupees implies that he is with a net sum of 0. And he also quits if he wins at least 3 rupees. So 3 rupees is one along with 3 rupees that he already had. So if he scores or if he has a sum of 6 rupees, he quits. Or if it's 7 rupees also, he quits. So there are 8 states in the Markov chain, which denote the sum of money that he has with himself. So they are at 0, 1, 2, 3, 4, 5, 6, and 7. Now we don't consider greater sums like 8, 9, and 10. For example, we don't consider 8 because that sum of money is never reached. Because to win 8 rupees, he must have already won 6 rupees. Because from the description, he wins 2 rupees at a time. So to have won 8 rupees in the current bet, the previous bet must have been at 6 rupees. So 6 plus 2 is 8. But we know that he quits on reaching rupees 6. So 8 is not attained. Similarly, 9, 10, 11, 12 are also not attained. And the money doesn't go in negative because he's never in debt. Because once he loses all the 3 rupees that he began with, he quits. So 0 is the minimum amount that he'll always carry home. And 6 or 7 is the maximum amount that he will carry with him. To describe this, I've written these two equations. The transition of the system from xi to xi plus 2. This is when he wins. He wins 2 rupees at the time. This probability is given by 1 by 4 as given in the question. But this is applicable only for states 1, 2, 3, 4, and 5. Because if he has 1 rupee, he will win and reach 3 rupees. And with 3, he will reach 5 rupees. And with 5, he will reach 7 rupees. This is okay. But having reached 7, he'll quit. Similarly, if he has 2 rupees, he'll go to 4 rupees with the probability of 1 by 4. And from 4, he'll go to a probability of, and he'll go to a sum of 6 with the probability of 1 by 4. But having reached 6, he'll quit. So xi to xi plus 2, the jump is 2 at a time because he wins 2 rupees. This jump happens with the probability of 1 by 4. And similarly, from xi to xi minus 1, if he loses with the probability of 3 by 4. And this is obtained when the states are again 1, 2, 3, 4, 5. Because if he is at 1 rupee, he will lose that rupee and go to 0. If he is at 2, he'll go to 1. If he is at 3, he'll go to 2. If he is at 4, he'll go to 3. If he is at 5, he'll go to 4. And if he's at 6, he'll go to 5. But if he's at 6, he'll not even play the game. So we do not write this down equation for the sum of money at 6 because if he's already at 6, he'll never bet any further. So this xi to xi minus 1 at 3 by 4 is only for the states 1 through 5. So what happens to the other 3 states, 0, 6, and 7? If it is a 0, 6, and 7, he's certain not to continue the betting. So if he is having 6 rupees, he'll never continue. The bet ends there. Or if he's already at 7 rupees, he'll never continue. The bet ends there. If he has 0 rupees, he'll once again never continue. The bet ends there. So with these three equations, we can define the TPM of this matrix. There are 8 states in this Markov chain. So the corresponding TPM is a large 8 by 8 matrix with 64 entries. And based on the equation that we just defined, we have the entries of this TPM as here. Clearly note down that the entries in the first row and the last 2 rows are 1 and 1 each. There is a transition only in the remaining 5 rows of the TPM. So with this information, we have understood what the question gives us. We'll move on to solving the problem. The problem wants us to find the probability that he places at least 4 bets. That is, the game continues for a minimum of 4 rounds. So to go to the fourth round or the fifth round or the sixth round, the game should not end at the end of the third bet. So the end of the third bet, the gambler has the money which is equal to 1 or 2 or 3 or 4 or 5, and this money should not be equal to 0 or 6 or 7, because if it is at 0 or 6 or 7, he'll quit and the game will never go to the fourth round. So to go to the fourth round, we are looking for the total sum of money with the gambler as 1, 2, 3, 4, or 5, and it should not be 0, 6, or 7. And since we talk about the third bet, this refers to the probabilities denoted by P3. And because the matrix is quite large, we will not try finding the third power or n cube. So we'll find P3 from P2, P2 from P1, and P1 from P0. And P0, the initial probability matrix, is a 1 by 8 matrix with these entries. It's 0, 0, 0, 1, followed by 4 zeros. Why is it of this kind? Because the question tells us that the gambler starts with 3 rupees. The gambler starts the game with 3 rupees. So it is certain that he has 3 rupees. So the system, the Markov chain, begins in the state of 3 rupees. All the other states do not have, the chain does not start with the other states. So the other states have a chance of 0, and state 3 has a chance of 1. And so we are trying to find out what P3 is. To find P3, we'll get P2 and P1. We'll do that in the next screen. P1, again, by the application of Chapman Kolmogrov equations, is the product of P0 and M. So P0, as we discussed, is this 1 by 8 matrix, and M is this 8 by 8 matrix. The result is a 1 by 8 matrix again, which tells us that he will win. He will win 0 rupees with a chance of 0, 1 rupee with a chance of 0, 2 rupees with a chance of 3 by 4, 3 rupees with a chance of 0, 4 rupees with a chance of 0, 5 rupees, 5 rupees with a chance of 1 by 4, 6 rupees with a chance of 0, 7 rupees with a chance of 0 again. But we are not focused on finding what P1 is, so we'll move on to the next time step, P2. And we know that P2 is P1 times M. So we just multiply P1, the answer we obtained in the previous screen, with the TPM. That's again a result. The result is a 1 by 8 matrix, and it tells us that he wins rupees 1, the chance of 9 by 16, rupees 4, the chance of 6 by 16, and rupees 6, the chance of 1 by 16. So rupees 7, the chance of 1 by 16. Once again, we're not focused on the second bet. We are, in fact, focused on the third bet. So we go to the next time step, which is P3. We know P3 is P2 times M. P2 times M. So P2 is the answer we just obtained. So multiplying P2 and M, we get another 1 by 8 matrix with 27 by 64, a couple of zeros, 27 by 64 again, followed by a couple of zeros, 6 by 64, and 1 by 16. Now this helps us arrive at the required answer. So the end of 3 time steps, these are the answers we have. So every probability corresponds to a sum of money that he has. So he has 0 rupees with a chance of 27 by 64, 7 rupees with a chance of 1 by 16, 6 rupees with a chance of 6 by 64. So if he has to continue for the fourth bet and or beyond that, he must not have rupees 0 or rupees 6 or rupees 7. So the sum of money that he has must not be equal to 0 or 6 or 7. So we discard the first probability and the last two probabilities from P3, which can be either of this, or this, or this. Adding them up, we have 0 plus 0 plus 27 by 64 plus 0 plus 0, and the answer is in fact 27 by 64. So that is a 27 by 64, which will denote the probability that he bets or the game goes on for 4 rounds or more rounds. So this is the case which I wanted to discuss because the matrix is so large. Finding the square of the matrix or the cube of the matrix is not a practically easy task. So we apply the Chapman Kolmogrov equations and arrive at the required answer. I hope you enjoyed this video lesson and follow this with another lesson very shortly.